A few announcements before we begin. Exam 1 is coming up on September 23rd, which includes modules 1 and 2. I was working on the exam and I thought I'll give out like a template for you to help prepare. Four problems, 75 minutes, two sheets of notes, handwritten notes, no printed material. You can't get a photocopy of your textbook or anything. Okay, only handwritten notes. The four problems will be distributed as one word problem involving a first order ODE, the material we spoke about in the very first lecture. The second problem or one of the problems will be to solve a second order ODE using the methods of chapter 2, which is essentially characteristic equation. And then third problem or one of the four problems is to modify or to manipulate Legendre polynomials or Bessel functions to prove an identity. So you can find these type of problems at the end of section 5.2 and section 5.4. So you should prepare for both. You'll be asked one of those, so but you don't know which one. Okay, it could be a Legendre polynomial or Bessel function. And then one problem to solve a second order ODE using power series methods. The coefficients may be functions of x, for which you will use either the methods in section 5.1 or section 5.3. Okay, so that way we cover all the topics we are going to be discussing. Maybe I can annotate here. This is sections 5.2 and 5.4. This is sections 5.1 and 5.3. Okay. Yes.
Given the series, like sample series,
What sample series?
like log x, sin x.
You are bringing two sheets of notes, right? Why should I give you anything?
So
you can bring the information you think you need. I'll provide for the problem self-contained information to solve the problem. So whatever hints you want, you bring it in your sheet.
So the series we need to bring it in our sheet.
That's up to you. I can't tell you what to bring. You can bring whatever you want. Two sheets of notes. Yeah.
Would you recommend writing the series, like logarithm and stuff as power series on our note sheets?
I would, if you have two sheets, that is four sides, it wouldn't hurt you to write it somewhere in the corner. Instead of thinking so much about it. Okay, so that is regarding the exam, which is coming up on 23rd. Okay. I have posted this on the canvas, but I'll repost it because I made some annotations right now. Any other questions? Okay, so that said, I will also briefly talk about the project that you're supposed to do based on module 2. Turn on the lights. So for project 1, I thought about it. It would greatly simplify your life. And also I was originally thinking about doing section 5.5, which is like an advanced topic on Bessel functions. But I don't want to do it because I want to spend more time on the sections 5.1 to 4. Okay, it's pretty lengthy. So what I'm suggesting is for project 1, you can choose any problem in this problem set. Out of 1 to 9, pick any one that you like, solve it analytically, and implement it as a computer code. If you're doing it in MATLAB or Python or whatever language, if it has built-in functions to calculate Bessel functions, do not use them. I want you to write your own subroutine to calculate Bessel functions. Is that clear? If I see a submission with using Bessel of X or whatever from MATLAB, 0. I'm making that very clear. Yes.
Can we use the function?
Yeah, you can do that, but I have to see your own subroutine with the details of how you built the loop to calculate that infinite series. Okay, so pick any one problem and implement it. That's your exercise. Okay, so this I forget when it is due, but that's on the syllabus. You can easily look it up. Okay. then that's when that is due. Okay. All right. So with that said, let's get into today's topics. So last lecture, we started a problem and kind of stopped halfway. Here is your Legendre's equation, 1 minus x squared y double prime minus 2xy prime plus n times n plus 1 times y equal to 0. This is Legendre's equation without assuming n is an integer or anything, just any value of n. And for this equation, the solution would be y of x equals c1, or let me just use the same notation the book uses, a naught y1 of x plus a1 y2 of x, where y1x is 1 minus n times n plus 1 over 2 factorial and y2, the function, the other basis function is x minus n minus 1, n plus 2, I'll move out of your way in 1 second. So this is the general solution for any value of n. And of course, as you know, y1 of x and y2 of x are called basis functions because they are two linearly independent functions using which the solution is constructed. Okay. And if you are going to look for values of n that are integers, say 0, 1, 2, 3, and so on, you can clearly see for even values, this series will terminate at some finite value. If we do n equals 0, for n equals 0, y1 of x reduces to 1. 1, because n is 0, right? y1 of x is simply 1, and y2 of x continues to be an infinite series where you will have x minus x cube, x plus 3, x plus x cube over 3, plus x to the 5th over 5, plus and so on up to infinity. So you can, if you can remember, I can't remember, but if you can remember, even values of n result in a polynomial for y1 and an infinite series for y2. You can easily see the contrary also. If you try for n equals 1, can you please write out what is y1 and what is y2? You just need to put n equals 1 in those expressions. You're going to get 1 minus x squared, right? 1 minus x squared. And then you have minus 1 times 2 times 4 factorial, or x to the 4th minus x to the 6th, and so on up to infinity. Is that correct? times 1 times minus 1. Is this correct? Third term. So you'll have, so this, I'm looking at this term here. So you'll have minus 1 times 1 times 2 times 4 divided by 4 factorial, which is 4 times 3 times 2 times 1. So I'm left with a 3. So this is x to the 4th over 3. And can you write the next term just to, so what is the next term here? This starts from n minus 2. The next term should start from n minus 4, n minus 2, n plus 1, n plus 3, n plus 5 divided by 6 factorial. And I have to substitute n equals 1. That will be minus 3, minus 2, 1, 2, 4, 6 divided by 6 times 5 times 4 times 3 times 2 times 1, and I'm left with a 5. Sorry?
Like minus 3 minus 1.
Minus 3 minus 1. So I'm left with a 5, and the next term comes with a negative sign. So this is just divided by 5. So that is the series. And y2 of x would be, what is y2 when you substitute n equals 1? Just x, only the first term. Everything else will have a n minus 1. This is only x. These functions are what we call Legendre's polynomial. So this is polynomial of order 0. This is Legendre's polynomial of order 1. You can do order 2, 3, 4, and so on. Okay. So this is a recap of what we did, kind of like a summary of what we did last lecture. And we did start one problem. So let's see if we can complete it now. Problem set 5.2, problems 1 and problem 2. They are really the values of n equals 0 and n equals 1. Problem 1 reads, if n equals 0, p0 of x is 1. We already got that. And we are asked to show y2 of x, which is this function. For problem 1, we are asked to show y2 of x is equal to half logarithm of 1 plus x over 1 minus x. This factor here, half logarithm of 1 plus x over 1 minus x, appears in the second problem also. So why don't we start with this and try to reduce this to an infinite series, which we can directly identify with y2. Okay. Can I erase this information? I think it's getting recorded, and I'll also post it on Canvas. Yeah.
For the project 1, we like just submit the analytical problem and the analytical solution and the codes are
Code and output from the code.
Or we don't need to write a formal report or.
I'll think about the report, but as of now, just take that you have to present your analytical handwritten solution, computer code, and output from your code. And the code itself, that is, you should submit the code which I can download and be able to run. It's a MATLAB script, I can run it and see. Okay. If it's Python script, I might ask one of the graduate students to help me, but trust me, I'll try to check your code. Okay. Okay, can I erase this? Yeah. Okay, so let's start with half logarithm of 1 plus x over 1 minus x, which is half times. What is the infinite series of logarithm of 1 plus x? This is the information that you think you'll need, right? This is x minus x cubed by 3 plus x to the fifth over 5 minus and so on up to infinity. Am I correct? See my notes. Yeah. And logarithm of 1 minus x, wherever x appears, replace it with minus x. So this is minus x plus x cube over 3 minus x to the fifth over 5 and so on up to infinity. So if I take the difference divided by 2, what am I going to get? I'm going to get 2x minus 2x cube minus or plus x to the fifth. So I'm going to get x minus x cube over 3 plus x to the fifth over 5. Is this correct? No. Correct. So I'm subtracting, so this should add up 2x oh, this is negative. Yeah, sorry. So I need to subtract, right? So this becomes 2x becomes minus what am I missing here? Are we having this series correct here? Can you help please?
I think in the minus state, everything is minus. In the second one, yeah.
Okay.
In the acute terms, terms.
Based on the notes, there should be some x square over
Okay. So I think the cause of confusion is the series. We just get the series because if we get it right, the problem is over. Yeah. Yeah. Yeah, please tell me that. Yeah.
Minus x square by 2 plus x cube by 3 minus x square by 4 plus
Okay, so this becomes then minus x squared over 2
x cube.
plus and so on up to infinity. So when I take the difference, all the terms which have the same sign go away. Okay, and the other terms add up, which leaves me with x plus x cube over 3 plus x power 5 over 5 because I've already factored in the half. So this expression is equal to this infinite series. Okay, which you can directly identify is y2. This is y2 of x. That is, you can directly see it's the same as y2 of x. Okay. That was problem 1. To show this is equal to y2 of x. What is problem 2? Problem 2 is to show y1 of x is equal to 1 minus half ln 1 plus x over 1 minus x. This is what we started last time. Sorry?
1 minus 1 by x.
X clone.
On my, yeah, you see that. 1 minus 1 by 2 times x times ln of 1 plus x times 1 minus x, which I can also take this series and write this is 1 minus x times x plus x cube over 3 plus x to the fifth over 5 and so on up to infinity. Or I can write this is x squared, x to the fourth, x to the sixth and so on, which clearly is equal to this y1. So if you look at the rest of problems at 5.2, just suggesting some problems here. Problem 12, problem 10, 6 to 9. Those are the type of questions that you can think about in proving relations regarding Legendre-based polynomials. It is a polynomial. It has some special properties. You should be able to manipulate and use it because when we do partial differential equations, whenever spherical symmetry problems occur, the solution will reduce to a Legendre equation and you need to be able to construct solutions. So what we see here will become useful 2 units down the line. Okay. Any questions? All right, so let's start the next topic, Frobenius method. This topic, Frobenius method, is, in my opinion, one of the most useful concepts you will learn in this class, because whatever we learn here forms the basis for solving PD. Like power series method is nice and easy, but it has very limited applicability. So whenever you have functions, whenever you have equations that are of this form, y double prime plus p of x times x are divided by x times y prime plus c of x times x squared y of y equal to 0. So whenever you have functions p of x and c of x are analytic at x equal to 0. When I use the word analytic, what do you understand? Is it enough if a function is continuous? Continuous and the derivative exists and is unique at that point. Okay, that is generally speaking analytic. So we have seen that b of x, it may be 0, but it isn't infinite. Okay, that is the implication. Okay, it is analytic at x equal to 0. So when we encounter equations of this form, okay, the Frobenius method is to say at least one solution to this ODE can be represented as y of x equal to x power r multiplied by an infinite series m equals 0 to infinity am x power n, where r is any number, real or complex. It's just any number. And m, of course, is a counter, so it has to be an integer. Okay. So we are focused on these type of equations, which you might ask, why are we focused especially on the coefficient here being x squared and this being x? Because these type of equations occur in applied physics quite commonly, and that is one reason to focus on this. Okay. You might ask, I might encounter other equations. Either you solve them numerically or you find other analytical techniques that are outside the scope. Okay, so here we are teaching you how to deal with a special type of equations with wide applicability. All right, so we have already assumed that these functions are analytic at 0. So we'll rewrite them as x squared y double prime plus x times b of x times y prime plus c of x times y equal to 0. Okay. So if you have any function b of x and c of x, you know how to express them as a power series, right? Suppose b of x is e power x, what do? It's 1 plus x squared over 2 factorial and so on up to infinity, right? If it is sine x, cos x, any elementary function, you know the power series, infinite series, or if it is any function that is not a polynomial, you can use the idea of Maclaurin's series to represent b of x and c of x as power series. Suppose b of x happens to be 1 over 1 minus x. You know this is 1 over 1 minus x power minus 1, which is 1 plus x squared plus x cubed plus and so on up to infinity. Any analytic function can be represented as a power series. So we can in general write b of x is b naught plus b1x plus b2x squared plus and so on up to infinity. B naught, B1, B2 are all known. How do you know them? If b of x happens to be e power x, what is b naught? 1. What is b1? 1. What is b2? 1 over 2 factorial. So you can easily compare and work out what b naught, b1, b2 are. And for our discussion, we will treat them as knowns. So b of x, c of x, you can represent them in this fashion. And we will not think they are variables, or they don't need to be figured out later. Okay. So if you, based on what we have seen so far, if this is your equation and you claim or you assume y of x equal to infinite series m equal to 0 to infinity am x power m plus r is the solution, what is your natural next step? Compute the derivatives and substitute it back into the ODE. That is our natural instinct, right? So let's do that. So you can compute that. Y dash of x is summation m equal to 0 to infinity m plus r m equals 1 to infinity m plus r am x plus m, I'm sorry, actually it's m equals 0 to infinity m plus r am x power m plus r minus 1. That is same as writing x power r minus 1 multiplied by the infinite series from 0 to infinity m plus r times am x power m or x power r minus 1. Just generate 3 or 4 terms of this series. M equals 0, m equals 1, 2, and so on. So m equals 0 is r a naught plus 1 plus r a1 x plus 2 plus r a2 x squared and so on up to infinity. So you got your y prime. Similarly, let's get our y double prime. Y double prime of x equal to, what will that be equal? Infinite series m equals 0 to infinity m plus r times m plus r minus 1 times am x plus m plus r minus 2, which is x power r minus 2 I'm going to write this as, to generate the terms, x power r minus 2 r times r minus 1 a naught plus 1 plus r times r a1 x. I get out of your way shortly. 2 plus r plus 1 a2 x squared and so on up to infinity. Right, nothing really complicated, just little tedious. Okay. So now you can substitute these back into the ODE. You can write x squared times. So I'm going to write x squared times y double prime. This 2 goes away. Similarly, x times y prime, this minus 1 goes away. So I'm going to write substituting x squared y double prime and xy prime, I'm sorry, I should say comma xy prime and y in the original ODE. So I'm going to get x power r multiplied by r times r minus 1, or maybe I should write that on the other side. Can I erase the other side? Other side? Okay. All right. So first term, going to be x to the r times r minus 1 a naught plus 1 plus r times r a1x plus and so on up to infinity. Maybe I write one more term. 2 plus r times r plus 1 a2x squared up to infinity. So this is first term. Plus, I'll write this as b of x times xy prime. What is b of x in general? B naught plus b1x multiplied by xy prime, but I think I got rid of it, right? Can somebody tell me xy prime from your notes?
No, or you know,
Louder, please. X power r,
RA naught plus
x power r, r a naught plus
1 plus R
1 plus r
A1x
a1x
plus 2 plus R A2x
a to x squared and so on. So this is the second term. Okay, and the third term, we're going to write plus c naught plus c1x plus c2x squared plus and so on up to infinity. What is y? Y is x power r a naught plus a1x plus a2x squared equal to 0. Okay, are we all up to here? What would you do next? What's the natural progression? Right side is 0. Equate the powers or coefficients of each power, right? You could have a function on the right side. The procedure will not change. You can represent whatever that function is as another power series or a polynomial. Okay, the procedure would not change. So the next step is to equate or equating the coefficients of x power r plus 1, x power r plus 2 on both sides. Now recall, r is unknown. A0, A1, A2 are also not known at this point. Okay. What about B0, B1, C0, C1, etc.? They are known because you know the function, right? Okay. Just making sure. So you can do that and set up equations. So if you start with R and you go up to R plus M, that gives you M equations to solve for A0, A1. Wait, that gives you M plus 1 equations. You start from 0. So that gives you M plus 1 equations to solve for A0, A1, A2 up to AM. You can go as high as you want until you see a pattern. Okay, it's an infinite series. There is no end to this. You have to stop somewhere. This will give you A0, A1 values or expressions, but R still remains unknown. Okay, that still hasn't been sorted yet. Okay. If you take the smallest power, if you take m equals 0, consider m equals 0, which talks about coefficients of x power r. What would that be? Just collect the coefficients of x power r and equate them to 0. Can I write r times r minus 1 times a0 from the first term? Because the next term will be x power r plus 1. So that is not needed for us. We are collecting only powers of x power r. From the second, I will have b0 times r a0 plus b0 times r a0. Similarly, I will have c0 times a0. And this must be equal to 0. Okay. This equation, of course, has a0. So you can write r squared minus r plus b0 r plus c0 times a0 equal to 0. Or you can write this somewhat r squared minus r times b0 minus 1 plus c0 times a0 equal to 0. You're trying to solve for r. Keep that in mind. Okay, we are trying to get r in this exercise. So it has come down to a quadratic equation, a quadratic in r multiplied by a0. Now, if I tell you for this Frobenius method to work at all, a0 must not be 0. If I'm making that as a precondition, what would the rationale be? Remember, you start with this. You start with x power r times a0 plus a1x plus a2x squared and so on up to infinity. I'm saying a0 must not be 0. Why? What if a0 is 0? What's the consequence? If a is 0, then x equal to 0 becomes a trivial solution. That's what you're saying. What were you going to say? Same thing. Anyone else wants to comment on this? So by constraining a0 or requiring it to be non-zero, we are just excluding the trivial solution. So obviously, if you make that assumption, this expression can be zero by only one way, which is for this quadratic to be zero. So we say, they give it a name. I think it's called the indicial equation. Indicial equation. Which is to say r squared minus r times b naught minus 1 plus c naught equal to 0. Or actually the book writes it slightly differently. R times r minus 1 minus b naught r plus c naught equal to 0. Plus b naught. Wait, how did it become plus? Yeah, plus b naught. I was the one who made it. So this gives you a way to calculate r, right? It's a quadratic equation. Obviously, you're going to get two values of r. Now, depending on the two values of r, which could be real or complex, you're going to have a taxonomy of cases. Okay, so a list of possible scenarios. That's what will follow next. Don't confuse this with the previous thing we saw related to characteristic equation. That is just taking that method works only for second order ODEs with constant coefficients. That is, there we assume P of x is simply B naught and C of x is simply C naught, and we didn't have these terms. This is different. This is applicable for a wider class of equations where the coefficients are allowed to be functions of x itself. Okay. All right. So there are three possible cases. Okay, and we'll see an example for each type of scenario. All right. So case 1, case 2, case 3. That's sound. Okay. Case 1, the indicial equation gives values R1 and R2, which are distinct, and do not differ exactly by an integer. That is, R1 minus R2 is not equal to an integer. Okay, R1 minus R2 is not equal to an integer. In that case, we write y1 of x equal to x power R1 multiplied by an infinite series m equals 0 to infinity am x power m. And y2 of x, the other basic function, is x power R2 m equals 0 to infinity. I'll call this am uppercase x power m. That's the nomenclature book uses, so I'll stick to it. We'll see one example related to case 1, okay? Just making the list first. By the way, this is given in theorem 2, page 182. Theorem 2, page 182. Case 2 is initial equation gives a double root, meaning R1 equal to R2. And of course, if it's a double root, it's a special case. You can write this R1 equal to R2 equal to half 1 minus B naught. So I'll just leave it, I'll just call it R1, okay? So the solution in that case is y of x equal to x power R1 summation 0 to infinity am x power n. That is one of the solutions. That is one of the basis functions. So we'll call it y1. The other basis function is constructed as y1 of x times natural log of x plus x power r1 times summation 0 to infinity uppercase am x power n. In your work, research or your job or whatever, if you have the time, you don't have to remember all these scenarios and tables, and every time you can start from the basics, set up an indicial equation, get the values, and then work out the basis functions and then go on. Especially in the exam, you don't want to do that because time is limited. Okay, that is why I'm giving you this like a list, and we are not really focusing on the details of how these are constructed. We chose to use this as a computational tool and not as trying to delve into the underlying mathematics in very great detail. That's been the spirit from the beginning. So at least if there might be some students who don't like rules or a instructor telling them follow this procedure and get here. But to make life simpler, if you go through this procedure and come to this point and you get the two roots, it just reduces to a lookup table situation. Instead of you having to derive this from scratch every time. That's all this. Not that you're not capable of it, but it's just a lot of time. Okay. Case 3. Roots. The indicial equation gets you distinct roots, but R1 minus R2 is an integer. They differ exactly by an integer. Integer could mean negative integer or positive integer, but it's an integer. And by convention, we use R1 to denote the larger root. So that larger root, so that R1 minus R2 happens to be a positive number. In that case, one of the basis functions is y1 of x, x power r1, summation 0 to infinity am x power m. And y2 of x is k times y1 times ln of x plus x power r2 summation m equals 0 to infinity am x power n. And k will be determined using boundary conditions, I think. So when you are working out your sheet for the exam, you got to have this information. This is going to be handy in solving anything related to Frobenius. Okay. Okay, so there was a topic in module 2, sorry, not module 2, in chapter 2 that I didn't cover, but now we are going to cover it like an example problem. So let's solve the equation where, oh, I don't have the original equation. Okay. So your generalized equation is x squared y double prime plus b of x times xy prime plus c of x equal times y equal to 0. Solve for x squared y double prime plus a times xy prime plus what they call it here by equal to 0, where we just reduce them to be simple constants instead of them being any functions of x. Okay. This equation is given a name, Euler-Cauchy equation. Not a big fan of names because I usually don't remember them very well. But the point of names is if you are in a particular field and you encounter certain types of equations commonly, you would talk about it either through writing or in speech with peers. Then you need a name. That's when this becomes important. So this might speak to somebody who is doing structures or membranes or vibrations or whatever. Just because I don't know it doesn't mean it's not important. Okay. All right. So what I want you to do is to solve this equation for A equals 1.5 and B equals minus 0.5. So this is a little bit unsettling for you maybe, because here we use B naught and C naught to denote B of x equals B naught plus B1x plus B2x squared and so on up to infinity. And C of x is C naught plus C1x plus C2x squared plus and so on up to infinity. How do you adjust your equation to insert 1.5 and minus 0.5 here? So by that nomenclature, B naught is 1.5, right? And B1, B2, everything else is 0. And C naught is minus 0.5, C1, C2 is 0. So my R squared plus R times B naught minus 1 is 0.5 and then plus C naught is minus 0.5 equal to 0, or this is 2R squared plus R minus 1 equal to 0. That would make this. Can you factorize this? R equal to 1? Yeah. Okay. And what is the other root?
minus 2 half.
I was incorrect.
R equals 2. I mean, I thought somebody will flash me the answer, but minus 1 plus minus square root of 1 plus 8 divided by 2, which is so it's either minus 2 or plus 1. Is that correct?
Minus 1 and half.
Minus 1 and half. Okay. 4ac, 4a times c. So square root of 9 is 3, minus 1 plus minus 3 divided by 4. Thank God I'm not taking any of these. So this is minus 1 or 1 over 2. Okay. So you have R values to be minus 1 and half, and they clearly don't differ by exactly an integer. So you have to pick case 1 to construct your basis function. That said, you still have to figure out what the coefficients AM and uppercase AM are. So there is still work to do. Problem doesn't end here. Right? So you would say y1 of x equal to x power minus 1, or I'll write it 1 over x times m equals 0 to infinity am x power m is a basis function. Or I should be more specific and say is one of the basis functions, one of the two basis functions. So that said, how do you compute the coefficients am? How do you compute? I mean, if something is a basis function, what does it mean? It means it should satisfy this equation, right? So you can substitute this function with the 1 over x into this equation and evaluate or get relations for am. If this a and this a are throwing you off, I'll call it alpha m. So substitute y1 of x into the ODE, into the Cauchy-Euler ODE, and work out alpha naught, alpha 1, alpha 2, and so on. The Euler-Cauchy equation itself has a special property which you're going to discover in a few minutes when you do this exercise. So this is nothing but y1 of x equal to m equals 0 to infinity alpha m x power m minus 1. So compute the first and second derivatives, put them back here and get values of alpha. I mean, it's just a constant coefficient. Not a function, just a constant. See, this Euler-Cauchy equation will simplify. It's going to give you essentially these coefficients are all except alpha 0, everything will be 0. You're going to see that. That is the property of this equation. But in general, you need to be able to work out these coefficients. Okay. So how do you do this? Y1 dashed equal to sigma m equals 0 to infinity m minus 1 alpha m xm power minus 2 y1 double prime. So this implies xy prime or xy1 prime is summation 0 to infinity m minus 1 alpha m x power m minus 1. And then this is x squared y1 double prime right. Should be as minus 3. So if you get it back together, x squared y double prime plus 1.5 xy prime plus or minus 0.5 y equal to 0. M minus 1 times m minus 2 alpha m x power m minus 1 summation from 0 to infinity. But the second term plus 1.5 times yeah, I could have just stopped here and say all this will just vanish. But you don't know that, right? As yet. That's why we are going through this exercise. Okay. Plus or minus 0.5 times summation 0 to infinity alpha m x power m minus 1 equal to 0. What is the, I mean, the summation runs from the same indices, the same powers appear under each summation. So you can directly say the coefficient of x power m minus 1 has to be 0. Which is like saying m minus 1 times m minus 2 wait, that won't get us alpha m. That won't get us alpha m. How do you start with, how do you work out alpha naught? Okay, let's start with alpha naught. What happens? You'll have minus 1 times minus 2 plus 1.5 minus 0.5 times alpha naught equal to 0. Okay, this is 2. Right? This is minus 1.5. So this is 2. This is minus 2. times alpha naught equal to 0 or 0 times alpha naught equal to 0. What does that mean? Alpha naught can be anything. It would still satisfy this equation. So what that first of all means is alpha naught is arbitrary. Alpha naught is arbitrary. Okay. The rest of it, if you consider any value of any power of x power m minus 1, you can write m minus 1 times m minus 2 times or plus 1.5 times m minus 1 minus 0.5 times alpha m equal to 0. Try m equals 1. What do you get? You get minus 0.5 times alpha m is 0, which is possible only if alpha 1 is 0. Try m equals 1, you get alpha 1 is 0. Same logic, try m equals 2, you will get a constant times alpha 2 is 0, which is possible only if alpha 2 is 0. For any other value of m, by the same logic, constant times alpha 3 or alpha 4 is 0, which makes any alpha m 0 as long as m is not equal to 0. I have a request to all of you. Please stop me at 6:53. Don't let Tuesday happen or Monday happen. Okay, we all were here until like 7:03 or something. I don't want that. You don't want that. All right. So, what is your conclusion here? Alpha naught is arbitrary, and everything else is 0. Okay. So this solution really reduces down to alpha naught times x power minus 1 or alpha naught divided by x. Okay. The same logic, y2 of x, if you start with m equals 0 to infinity, I don't know the Greek alphabet alpha, but let me try. I call it AM. So this will also reduce down to, sorry, x power m minus, what is the other root? Half. So this will be m plus half, or this is a naught root x. So to put the closing screws, the solution to this equation is y of x equal to alpha naught over x plus a naught times square root of x, where both alpha naught and a naught are to be determined from boundary conditions. To be determined from boundary conditions. So this was a example in which we had constant coefficients, and that led to the so-called Euler-Cauchy equation, which is independently discussed in section 2.5, which we skipped over. and the solutions happen to be C1 x power R1 plus C2 x power R2. That's what this is. C1, C2 are arbitrary constants. Okay. So we have about 6 minutes, not 9 minutes. Let's try another case where you get a double root. The equation is, this is example 2 on page 183. X times x minus 1 y double prime plus 3x minus 1 y prime plus y equal to 0. This problem also proves to me I shouldn't discuss or make an exam so far out ahead. This was on my test, but no more. I got so interested in the problem that I had to discuss it today. No more on the test. All right, so we have time to form the initial equation and get the root. Can you please try? So you can write this equation y double prime plus 3x minus 1 divided by x times x minus 1 times y prime plus 1 over x times x minus 1 times y equal to 0. To match it with the functional form or the standard form, y double prime plus b of x times over x times y prime plus c of x over x squared times y equal to 0. So how do you then what is b of x? B of x is 3x minus 1 divided by x minus 1, and c of x has to be, what is c of x has to be? X divided by x minus 1, correct? No.
1.
Sorry,
You make the point.
was correct?
Let's divide it by
X divided by X minus
x by x by.
It was correct. Oh, it was correct, okay. Yeah. So this is your b of x and c of x. Quick question for you. How do you turn these into power series?
X minus 1 to the power minus 1.
So you want to write this as x times or minus x times 1 minus x power minus 1. Is that what you were saying? Okay. So you know this as a power series, or you know any polynomial, you can easily turn that into a, any rational function can be turned into a power series, which is minus x times 1 plus x squared plus x cube and so on. Or this is minus x squared minus x cube minus x to the 4 and so on. Which begs the question, what is C naught? C naught, 0, which gets you C naught to be 0. Okay, similarly, let's do this for the function b of x. The time. 51. Okay, I think we should stop here. So b of x is 3x minus 1, or I'll write it as 1 minus 3x times 1 minus x power minus 1, which is 1 minus 3x times 1 plus x squared plus x cubed, and so on up to infinity. So you can write this. This is an infinite series, of course. 1 plus x minus 3x, so minus 2x, plus x squared minus 3x squared, so that is minus 2x squared, plus x cubed minus 3x cubed, which is minus 2x cubed, and so on up to infinity. Which gives you b naught equal to 1. So let's get to the next step and stop, which is the initial equation is r times r minus 1 plus b naught r plus c naught equal to 0. Am I correct? Yeah. So r squared minus 1 plus r, I'm sorry, r squared minus r plus 0 equal to 0. R happens to be 0 and 0. Is that correct?
Yes.
Okay. So let's stop here and pick this up from next lecture.